Thanks, Chris. Can you guys hear me? There we are. So, yes, I'm from Montreal Python, and the first thing I want to get through before we talk about communicating sequential processes is I'm so excited to be here, and I am also excited because PyCon US is going to be in Canada next year in 2014 in Montreal, and I hope to see you guys all there. So, let's get started. I want to talk about this idea called communicating sequential processes, and it's an idea of how to do multi-core programming. And the reason why we care about this so much is that classically, Python programs have been written very sequentially to take advantage of one CPU, and we've been able to do this for a very long time because we've been taking advantage of Moore's law, where we can shrink processor dies and make things go faster. And unfortunately, two things have happened. One is physics, and so we can't do this anymore. And two is that we want to carry our super powerful computers in our pockets now, and we don't want our pockets to cook our precious things. And the other thing is that we don't want our phones to only last for 15 minutes. So the trend is that you're starting to get lots and lots of cores. Like we're starting to see 4-core and even 8-core in tablets now, but they're really slow in comparison to our desktop machines because they want to save power. So people are saying, well, okay, let's write multi-core programs. And multi-core programs, they're not particularly easy to write in the classical way. Like a lot of people learn how to do things in terms of multiple threads, and you share a chunk of memory and use locks to go and communicate between things. But a lot of times, that's not what you want to do. You want to go and do the communication between multiple single programs that you can reason about and have them pass data between each other. And the method of doing that is communicating sequential programs. So CSP is what I'm going to talk about. The first thing I'm going to do is basically talk about how to do this in Python. Like a lot of people think that concurrency in Python is hard, and that's not true. And hello, computer. There we go. We're going to look at a simple program. This simple program is basically like a downloader. It goes, if you take a look, it'll take some things on the command line, some URLs on the command line, and it'll go and get them. So we call download with the arguments. Download just basically runs through a generator. If you went to a talk earlier, you have learned about that. And it goes and fetches the response out here and prints that content at the end. And this is like your standard sequential program. And it works pretty well. Like if I'm lucky, the Wi-Fi will be working here. That's not what I wanted. I want two of these like this. Okay, terminal. And let's go and just run this program, example.py. And of course, we're going to use the Python website and maybe like some of the sponsors. You can thank me later, guys. Oh man, I'm so forgetful. Okay, let's go and grab these three. You can see this is a 2-core machine, and ooh, the network situation. Uh-oh. All right, you're going to have to trust me when I say this. It's a 2-core machine, and what's going to happen is, if it gets around to it, it'll go and let's try that again. Let's see if that works. It'll go and try to pick up 2013 PyCon 500pix.com, and then it'll stop because it's waiting for this stuff to happen. And then it'll go like one at a time. Even though it's a 2-core machine, it'll go this one stop and wait, this one stop and wait, and this one stop and wait, because it's only running on one core. You know what? You're just going to have to pretend that this works, okay? So if I want to go and turn this into something that uses both of the cores on my incredibly slow laptop, we're going to have to make a few changes here. And for something as simple as this program, where you have basically a downloader function that just goes and takes all of the URLs and sort of maps them to this URL getter, we can go and use something in the standard library. I think it's there for at least 2.6, and it's in Python 3. We're going to use multiprocessing.pool as an import, and then we're going to go and spawn off some threads in a thread pool. So we're going to say threads.multiprocessing.pool.threadpool. Now, this thing doesn't actually exist in the documentation, but it is there. It actually looks like the .pool sort of constructor there, which does process pools. I'm not going to go into the differences between process pools and thread pools right now, but we're going to go and return threads.imap URL get URLs. And imap here looks like basically the itertools imap, where it's going to go and apply the URL get function with the elements of URLs. If we run this, what will happen is it'll go and take the first couple, it'll basically run through the first URL and then immediately go to the second URL and fire off. Once one of them returns, it doesn't matter which one, the first or the second URL, once one of them finishes getting, it'll queue up the next one and so on and so forth. And here, this is a simple way of doing this. And in fact, underneath the hood, what threadpool is doing is it's maintaining queues to do this communicating sequential process. The processes here are that there are now 2 URL get threads, which run independently, and they basically go and talk to the main thread, the main process, and they talk. Basically, the main process tells the URL get threads what to do, and then they tell it the response. So it becomes almost like a pipeline. Now, if we want to see what happens underneath the hood, because it's better than just magic, you want to understand what's going on, we're going to actually decompose this into what it actually is doing. So URL get basically, instead of taking URLs, it's going to take an input queue and an output queue. And those are basically channels. So q.q and q.q. And this means I have to go and import. I'm going to stop using this. Import q. And then we're not going to do this anymore because there's no implicit. Sorry. We need to loop through because we're not going to use the thread pool anymore. So this thing has to go and read from the input. So we're going to say URL is equal to the get out of the input channel. It's going to go and read the response. And instead of returning, because we want this to run forever, we're going to go and put the content. And I'm just going to associate the URL, the input, with the content so that we know what's going on the other side, because this stuff can come in and out of order depending on how many CPUs are running. If there's only one, then it's going to it's going to return in the same order that it fetches. But when there's multiple stuff, that's not going to happen. So here, we need to actually call URL get instead of using this threads thing. So we're going to say we're going to spawn off we're going to spawn off a thread for each sing.cpu count for each of the things that threading.thread. We're going to start a new URL get thread. We're going to pass in the input and output. And when we say daemon is true, it means that even if this thread is kicking around when the process exits, we're going to let Python kill everything. And then for threads, you have to start them. Good. So now that we have these threads started, we're going to fill the input queue with the URLs. And then we're going to go and yield out the results. Because here, of course, we need to basically, this needs to look like an iterable. So if there are no unfinished tasks left, and the output queue has been consumed, so we're just going to repeat this until all the work is done, basically. And if I could run this, you would basically see that it goes and does this thing exactly like what the thread pool would do. Instead of actually using the built-in thing, the helper, we're going to go and do this by hand. So this is the underlying thing. There's more complications inside the standard library thread pool, but that's to protect you from some corner cases. I think we're going to do questions later, so if you don't mind saving them. Why would we want to do this? Well, this gives you a little bit more control about the underlying system. When you use thread pool or pool from multiprocessing, you can't actually go and control sort of how things pipeline through. There's only a simple map, and you got to wait for the result at the end. So, for instance, if you wanted to go and skip some code examples. If you wanted to go and take the result of this instead of just the content, and you wanted to post-process this, one of the things you could do is actually, one of the things you can actually do is chain these guys together. So, for instance, we could develop a hasher. If I wanted to compute the hash to know basically whether or not something is changed, then I could also go and write, let's say, content equals i.get, and then we're going to say the hash value is, let's say, hashlib.showoff512, which is really slow, and then hash that content .hex digest, and then put that into content into the output. So here, this is hashed, and i.task done. So here, then, we would not only start up the queues for the download, but you can also go and start up the queues for the hasher. And then what happens is, we got to hook this up correctly. I'm going to go and turn this into queue. And we're going to hook in. If you see, I'm replacing the output of something into the other. So you start, here with the input. It goes into the queue. It can fall into another queue and come out. And you can chain these things together. So when you go and put stuff in here, while the unfinished tasks, as long as there's nothing unfinished, and I haven't consumed everything, this goes in chains together quite well. Now, this is a little bit complicated, I have to admit. You are using threads or processes directly, but if you go and implement this style of functions that take input and output queues, you can start doing the multiprocessing very conveniently, even though it's a little bit of extra boilerplate. There's not good first-class support in Python, but it is quite possible. And the advantage of doing it this way is that these functions are really, really simple. Like, it's hard to go and make a mistake here. Everything that comes in is basically coming in through the channel, through the queue, and there's no shared state in the rest of the system. The reason why you don't want shared state in the rest of the system is then you have to go and worry about locking, worry about basically whether or not some other thing is going to trample stuff, and worry about live locks and deadlocks. In here, basically each thread goes and takes something, does something to it, filters it through, and spits it out, and it doesn't have to worry about the external state. If you do want to worry about external state, then almost the best way to do this in this programming style is to have these communicating processes funnel into something main that goes and handles the state before farming it out to other processes again. OK, so I was going to go through some extra examples, but I think we're out of time. So there are these sample programs that do run on your computer if you have a reliable network connection. And they're going to be available on the pycon.ca GitHub, which I suspect is going to be something like http.com/ You guys should use HTTPS. Let's be paranoid. On .ca, is that right? No dot. Oh, this is not valid code. Thanks, Emacs. But that, you will be able to find my notes and all sorts of other people's notes. So you should definitely watch that repo. Any questions? Yes, sir. I'll just wait for the mic.
Hello. Is the queue implementation you're using thread safe? Is it like gonna block if it's empty, or are they buffered?
Yes.
Or?
So the queue here comes from the standard library. It is thread safe, but it's not cross-process. If you want to use queues that are cross-process, instead of using queue.queue, you use multiprocessing.queue. That crosses processes. So let's say you want to go and read up on the difference between threads and processes as a trade-off inside Python. Multiprocessing.process basically allows you to run multiple CPU-intensive tasks side by side, but the difference is that there's communication overhead. When it's queue.queue and threading.thread, you can't do two CPU-intensive things inside Python. You can definitely use a C library or a built-in function that's implemented in C. Those will juggle properly. But for this, you have queue.queue's overhead is much lower because it doesn't have to talk interprocess. Any other questions?
Thanks for the talk. Beyond the notes that you're going to have up on the GitHub, do you have anything that sort of explains ways to use this style, or is there any documentation out there on the internet that you could point us towards?
There is. So there's, if you go and take a look at, if you Google for communicating sequential processes, there are actually quite a few resources on how to program this way, but not specifically in Python. So as long as you can read other languages, you start to get to feel about sort of the methodology behind it and why it's a good way of doing it. You can also take a look at alternative ways in 3.4 if you're lucky enough to be able to develop on it. There's Concurrent Futures, which is the opposite way. So Concurrent Futures lets you pull data into the future, whereas this is pushing data through a pipeline. But both of those are ways you can use both of those in Python, and I encourage you guys to check it out instead of just writing sequential programs. Do we have time for one more question? Anybody? No? Well, thank you very much. And
Yep. Thanks, Simon.